I'll make the same mistake I did last week. Okay, so this week we're going to discuss simulation analysis, and I think I sent out this handout where we talk about simulation analysis. So I'm not sure if you have kids, but if your kid has these Nintendo games, then they're more of an expert at simulation than you are. They are excellent at this. And these games are really just simulation games. But they're only games. They're only games. You could see down here that I have a couple examples of flight simulators. So you see on this one, single seat, and the three screens are trying to simulate what you see out of the cockpit. And this one on the right, same story, but now you have probably a pilot and a co-pilot. You can buy this type of software yourself. It's called Flight Simulator. Not very expensive. And the Flight Simulator will do a very good job of helping you to learn how to fly. So let's ask this question then. What is simulation analysis? What is simulation analysis, right? So it's an imitation of real life processes over time. I should have underlined over time there. So simulation requires the use of models. The models represent or excuse me, the models represent or simulate real life processes. Real life processes. And what does simulation mean? What does simulation mean? Simulation is the evolution of this model over time. So over time is the key there. In real life nowadays, computers do the simulations, and many of them do an excellent job. And simulation is also done a lot for educational purposes. Okay, so when we talk about a model, what does that mean, a model? It goes out there and it tries to replicate how a system will work in real life. And at its fundamental roots, simulation analysis uses a lot of math and calculations to predict what's going to happen on the future based off data from the past. Fundamentally, what is simulation analysis? Basically, simulation analysis is a data generation technique. So the simulation that we want to look at today is going to generate data. But that's the way it is with all simulations. One of the drawbacks of simulations, or one of the benefits of simulations, is that in real life, it could be time consuming, it could be expensive, or it could be destructive to conduct a real life study. So a real life study of a situation or a problem. Okay, so you can see the example that they have there. They have a riverbank and they want to build some type of, not a riverbank, just your typical bank. And you want to determine service requirements. So we saw that last week when we were doing the queuing models. So the use of simulation then frees the programmer and user from having to observe a bank and keep track exactly when each customer arrives or leaves. Simulation is used when actual experimentation is not feasible. Simulation is used when actual experimentation is not feasible. Actual experimentation is better. Actual experimentation is better. But in many cases, actual experimentation is not possible. So the next best solution is simulation analysis. And that's what we want to do today. Here up here is a nice graph of what simulation is. In many cases, it's repeated trial and error. So we want to determine the behavior of a system or look at different parts of the system. In a simulation model, it's a mathematical model that calculates the impact of uncertain inputs. Basically, what conclusions can you draw because uncertain inputs are being fed into the system? So a simulation model will include inputs that are uncertain numbers or uncertain variables. And we'll try an experiment like that today. Intermediate calculations are required. We're going to do a real simple calculation, but these calculations, they can get extremely difficult. Model outputs depends on the inputs. Basically, the outputs are uncertain because the inputs are uncertain. In other words, you can't predict these outputs. So you want to run simulation to give you an idea of what the potential outputs will be. Now, we have, on this page, we have two. The basic process is the same, but you have discrete event simulation versus continuous. So discrete event simulation is what will happen at 1 o'clock, 2 o'clock, 3 o'clock. Continuous means it can happen anywhere in between 1 to 2 o'clock. Very simple and almost too simple of an explanation, but that's the difference between discrete and continuous. A better example I can give you of a discrete simulation is when you roll a dice. And when you have a dice, there's only 6 outcomes, right? Just one dice. 1, 2, 3, 4, 5, 6. You can't get 2.5. You can't get 3 1/3. You can't get 5 1/2. It's only 1, 2, 3, 4, 5, 6. It could be those discrete answers. Versus for continuous, within a given range, you can be, let's say between 1 and 2. It could be 1.1. Then the next one could be 1.1.1. And the next one, 1.1.1.1. You get the point. It can be any number up to 20 decimal points within that range. That's continuous. That's a continuous one. So we'll let the computer go out there and select the value for our random numbers that we want to input into the simulation. So what is computer simulation then? Computer simulation, you want to imitate a real life system or process. All of that is modeled in the computer. This is performing experiments on the computer to understand the behavior of the system, or to maybe go out there and evaluate a new strategy. So then you go out there and you observe events, processes, properties, and behavior of the system with this computer model. Here's another good chart here. It's an attempt to imitate reality. Simulation is used in many different situations. And a computer model is the mathematical representation of the functioning of a process, concept, or system. All of this is done through a computer program. So we're going to try today. It's going to be a very simple calculation and formula that you use. Understand that, especially when you're doing real life business situations, it'll be much more complex than what you have on your Nintendo system that the kids use. Much more complex. Could take a ton of computer time, but the simulation could be mathematically very complex to try to imitate a real life process. Okay, and so in this particular case then, we have a couple of more slides on computer simulation. Says the same thing. I like this slide right here because you can see there that what is this simulation trying to imitate? A crash dummy or a accident. What type of protection are you going to get from your car? And this is just me guessing here, but it looks like right here you have an airbag. Even if you were going to do an experiment, you've seen those type of experiments where they go out there and they run a car into a wall. Very destructive, very destructive. The good thing about a computer simulation is that if it's accurate, you can run the simulation many times so that you get a good idea of the outputs of the system. In this particular case, how effective is the collision safety equipment in a car? Okay, and so in this one then, even if you were just going to run a chair into a wall, that's going to be expensive and destructive. Computer simulation could save you a lot of costs. Okay, so the next question then is, when do you use simulation? When do you use simulation? I have there when experimentation is not possible or not feasible for some reason. A real life experiment is better than a simulation. However, if the real life experiment is not possible or is very expensive, simulation can be a very good second choice. Now, a second condition for using simulation is when the analytical solution procedures is not known. If you have an equation that will do the prediction for you, Well, you don't need simulation. You don't need experimentation. But if you don't have those procedures down mathematically where you can calculate the answer mathematically, simulation models are the way to go. And you can look here. All right, so you have a problem. You can't do an experiment because it's too expensive or it's impossible. So what do? You have your problem, you have your model, there's some trial and error that's involved, you have an improved model, and then you come up with whatever solution you are looking for. But again, simulation comes after experimentation. Experimentation is better. But again, experimentation could be too expensive or impossible to do. So I have here a couple of slides. These are pretty good slides. And they go out there and they discuss what the simulation procedure is. And the one thing to get from both of these is that this is an iterative process. You'd like to be able to go from A to B in one step. But in many times, what do you have to do? You have to go out there, modify the simulation, run it again. And if you analyze the results and they're feasible, you're finished with the simulation. But the process of modifying the simulation, that's a big point. Could take a lot of time and effort. So more slides here of processing, simulation. These are pretty good. I'll give you a chance to read these on your own. And even more. Again, with the emphasis that simulation is an iterative process. All right? There are different, when you understand simulation, you can categorize them into different types. So you have probabilistic simulation. We're going to try that today. Time dependent, time independent simulation, where time is a factor. Visual, interactive simulation. These are the games that the kids play. Okay? And kids many times are very good at this. They are experts at simulation without understanding everything that we're going to. And then the ones that we want to focus on are business games, game theory for simulation, but as it applies to business, corporate, and financial simulation, we're going to try this as our problem today. Okay, and this corporate, the business games, the corporate and financial simulations, don't be fooled by the easy example we do today, because these can be tremendously complex and tremendously complex and difficult to construct. But like anything else, the better the job you do, the better the predictive ability of your simulation. Okay. So again, we have here types of simulation: visual, scenario, discrete. We're going to do this. Numeric, corporate and financial simulation. Okay. This is a good one from a pure math standpoint. But when you're going to use numerical models, ultimately, you want to run simulation analysis to determine how effective your simulation is going to be. Here I have slides that will talk about different applications of simulation. So I won't go over them individually, but these are pretty good slides that show when simulation is done and in these areas, how they have become very effective and an indispensable planning tool. Here's more slides. Here's more slides of applications. I just found a whole bunch of these, and while there is some overlap, each slide is pretty unique. We're going to do business simulation. They talk about here queuing models. How you go out there and study a simulation, experiment, mathematical models. We want to look at simulation here based off our mathematical models. Okay, what are some of the advantages of simulation? When it's programmed correctly, okay, it's free from going out there and doing the math. The computer will do that for you. Simulation models are pretty flexible, and they can be easily well, maybe not easily, but they can be modified to changing situations. Other advantages of modeling in situations: safety. Okay, you're not going to hurt people or the environment. Economic savings, projections, the predictive nature of simulations, visualizations. You can see that a well-constructed simulation will help you see the results. And replication, you can go out there and do many, many, many different scenarios. All right? These slides will talk about the advantages of simulations: to test, to predict, to train, to investigate. This is a good slide down here. This slide up here, more complete, but this slide down here does a good job of explaining the advantages of computer simulation. Of course, simulation is not without its faults. It's not without its faults. Okay, you can look here and look at what some of the shortfalls of simulation are. But right here, we're going to do Monte Carlo simulation in real life with complex models. The cost, the computer cost, can be extremely high, okay? Because you know that runtime on a computer can be expensive, and all the programming that has to go into constructing that model with all the software engineers, very, very, very expensive. Okay, so that's really the main criticism of simulation analysis, is that it's just so expensive to do. Even though it's safe, even though you can replicate it, it's expensive to do. And here I have more. Okay, I have more. And you can see at the top here, what's the first thing this one says? The models are expensive. Okay, and in this one down here, the modeling requires special training, a lot of programming, potentially, that's involved. Now we want to go into today we're going to try something that's a little bit more of a categorized even further down. This is called Monte Carlo simulation. And Carlo simulation. Monte Carlo simulation, fundamentally, you're going to use it to assess risk. And what it does is that it's going to go out there and look at different probabilities associated with the inputs. What risk do those uncertain inputs inject into your business, the product you're trying to develop, so on and so forth? That's what Monte Carlo simulation is. It's injecting an uncertain variable. Okay, so what is Monte Carlo simulation? We're going to do repeated random samplings. And some of these big companies, how many times do they go out there? They make this really complicated model. And when I say repeated random samplings, how many times do they run it? For some companies, I've read that at a minimum, they're going to run that equation, that set of equations that take up about maybe 20, 30 pages of computer code. They'll run it millions of times. It's the randomness that's important. They want to see the random nature of the results. Okay? Oh, I should change this. Often used in physical, business, and mathematical models. So you can add business here too. It's best when it's difficult or impossible to use other approaches, and it's used for optimization and integration. So there's a general pattern. We have to define what the range is of possible inputs. We want to generate inputs randomly from a probability distribution. We go out there, run it many times, and finally, we're going to aggregate the results and try to come up with conclusions. Okay, so here then, we have the Monte Carlo system of simulation. Again, you're putting random numbers into your mathematical model. Then you run that model in real life for these big companies. They're going to run that model sometimes millions of times. Okay? And based on my experience doing this, what are these programmers doing when they run these Monte Carlo simulations? They know that the busy time computer-wise for their company is from 8 to 5. They're going to run this many times. So these guys then, they start the computer simulation at 6 o'clock in the evening, and it's going to run many times. And they go out there and say, run it as many times as you can from 6 a.m. to 6 p.m. Oh, I'm sorry, from 6 p.m. to 6 a.m. when your computer system is not busy from your everyday operations. Because this simulation analysis is going to eat up so much computer time, they want to dedicate a lot of, as much computing power as possible without going out there and disrupting everyday operations. Okay, here are some Excel commands that you can use for our Monte Carlo simulations. Really good slide here that talks about how Monte Carlo simulation works. Okay, so you can read that later. Very good slide. Big picture. Okay, you have random inputs. The outputs are based off many iterations. You can have different probability distributions for your inputs. These are the steps in the Monte Carlo simulations. Okay, a slide that just shows the processes. We saw this before, but now this is including the Monte Carlo simulations, and you're just going to just keep running it many times, many times. That's what n is equal to n plus 1. In other words, it's going to go from 1 to 2, then 2 to 3, 3 to 4, so on and so forth, until it gets run millions of times. We talked about probability distributions. So in this simple example, they have this probability distribution for, I forget what they're making, a cake or something. What's the probability that there's no demand for the cakes? 1%. 15. Demand for 15 cakes, 15%. 25 cakes, 20%. Where'd they get all these numbers from? Probably from observation. Probably from observation. Okay? We know that pilots, yeah, I was trying to find one with pilots, not just Air Force pilots, but pilots use flight simulators a lot. So this one, I'm sorry, this one talks about wartime simulation. I don't want to talk about that, especially in this environment, but many times pilots use simulations to get ready to fly the plane. Okay, so let's go out here then and let's try our Monte Carlo simulation in Excel. Okay, and we'll just make these in millions. But here's our mathematical function. Q squared minus 25Q, where Q is the number of units sold. The number of units sold is going to help us determine whether there's going to be a profit or a loss. And in this particular case, these are just given. These are just given. They didn't come from anywhere. But we're going to have, on average, 27 units sold, or 27,000, 27 million units sold. We'll just keep it 27 so the numbers don't get too big. And the standard deviation for this mean or average is going to be 4 units. We'll run 10 iterations, and we want to look at, we'll see how many of these we can get, these key performance indicators. So you're going to see then that I'm going to use if then else statements like you do in computer programming. Okay, so let's keep this up. Here we go. Okay, and so hopefully you can see this. But right here, I'm going to have Q. Make this bigger. I'm only going to run it 10 times. Q is going to be the number sold. We know that. The profit function Now, this profit function in real life could be tremendously complicated, but we just want to keep it simple for now. So we'll just make this 0 for now, okay? And from the previous page, we know that the profit function is q squared minus 25q. Q squared minus 25q. So that if this is q, then q squared, this is going to be equal to this cell squared minus 25 times this cell. It's going to be 0 for now. It's going to be 0 for now. But if we make it 1, then that's going to be 1 squared minus 25 times 1. If we only sell 1 unit, we're going to lose $24. You see how this works? Okay? So now, then in this particular case, we'll just leave this out. Let's clear this for a second. And we want to run 10 iterations. 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll run 10 iterations. The Q will be a random input. We'll assume that Q is normally distributed, mean of 27, standard deviation of 4. That's a random input into our system, Q, the number of units sold. All right, so here we go. Let me make this a little bit bigger. Okay, and so now we want to inject random numbers here. We want to inject random numbers here. Okay, so how do we do that? So we want to go data, data analysis, I want to choose random number generation. Hopefully you can see this. Random number generation, hit OK. How many variables do I want to choose? In this case, it's only one, Q, but you can choose a whole lot in real life. So we're only going to choose one. How many of these are we going to do? We want to do 10 of these. What type of distribution are we going to run? We want to run the normal distribution, and we have to input a mean of 27. That was given to us. 27 with the standard deviation. I think it was 4. I'll go back and look. Okay, random seed, you can just leave that blank. But now the output, where do I want it to start? It's going to go start here and go down. So I want to put it right here. I want to start at D9 and go all the way down 10 times. Okay, so my quantity produced is going to be my random variable, normal distribution with a standard deviation of 4. How many times are we going to be profitable or lose money? So here we go. Okay, so you can see then that based off these quantities sold, These are our estimates of what the profits are going to be. These were random inputs. These are random inputs. And now this is what we estimate the profits would be. What we estimate the profits would be. Okay, so there's our output. Let's see how much of this analysis we can do. Okay, and now I'm going to do if the, oh, not yet. Let's hold on. Minimum, maximum, range. Minimum, maximum, range. Okay, so of this, of our potential profit numbers, what is the minimum? So the minimum of the profits, what is the Excel function? Equal, I think it's equal min, left parentheses, highlight this vector of data, right parentheses. In other words, we want Excel to help us find the minimum number. Now, you can eyeball that. You can eyeball that and see it's going to be that negative 36. But what if you had run this 1,000 times? Boy, that would be hard to eyeball. And even more. Okay, you can run it in Excel, I forget. Maybe something like 2 or 3 million random numbers. But in our case, the minimum is this 36. The maximum of our simulated profits the maximum, same thing. What's the maximum number we can get? Equals max, left parentheses of all of these. What's the biggest number we can get? And again, you can just eyeball it in our simple example. But it's 282. 282. What is the range of profits we can potentially get? We have range. That's going to be equal to the maximum minus the minimum. So it's minus a negative number. So what's the range of profits we can get? 282 minus 36. Our profits have a total range of 319. 319. Okay, let's see. So what do we got to do next? So number of, how about this? Let me do these, but let's do these. Overall average of profit function, and what is the median? What is the median? All right, so we know that this is the minimum, maximum, the range. What is the mean or average that we can get? Let's make this a little bit smaller. Okay, so the mean or average, how do you do that in Excel? Equals average. What is the average profit from our simulation? on average, we're going to get a profit of $87. What is the median? You know what the median is then, right? The median is the number where half the observations are above, half the observations are below. So here then we have the median. Okay, and what is the Excel function? Equals median. And again, highlight this vector of data and hit the, so it's 61. We don't have 61 here because this is a calculated number, but at a profit of 61, half of the observations are below $61, half of the observations are above. Okay, so next one then is, what percentage of occurrences of net income, net loss? Okay, and so here's where the if then else statements come. All right, so let's just put up here. We'll skip a column. We have, and let's just say yes is equal to 1, no is equal to 0. Okay, and so here then, this column will make this net income, and we'll make this one net loss. So we want to search these and figure out if it's a net income or net loss. So how about this? So here comes the if statements in Excel. So equals if this cell is greater than 0. Where's my greater than sign? Is greater than 0, then you put 1. Else, you put 0. So if the profit is greater than 0, you put 1 for net income, 0 for no, it's not. Okay. So here we hit enter. 1, that makes sense. This is a profit. We can copy this all the way down. This works. Yes, yes, profit, 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 profit. Loss, no. Profit, profit. So it looks like it works. We can do the same thing here. If this is less than 0, it's a net loss. You put comma 1, else 0. Okay, let's copy it down. And we see here, we have 1 net loss. Okay, so let's put a total here. Equals sum. 9. One. Okay. We have the count. How many simulations did we run? Okay. So equal count. Should come out to be 10. That's n, the population size or sample size. Okay, and right here we'll put percentage. We'll put percentage. Okay, and then right here then, what does this key performance indicator tell us? I'm going to do equal to the total divided by the count. Okay, and let's put this as a number. So basically here, our simulation ran a net income 90% of the time. And same token here. It's just going to be, if it runs a net income 90% of the time, then it's going to run a net loss 10% of the time. So you have to go out there and do these, you run your simulation first, and then you do these types of metrics to help you determine if you had a net income or net loss, what the range is, so on and so forth. But whatever you want to go out there and try to measure, you run your simulations, everything looked good, then you have your metrics. Okay, so I'm sorry, we kind of ran out of time. I'll do the rest. Let's see. I'll do the rest. Average of net income, average of net loss. I'll do those. I'll put them into our spreadsheet and put them into a Blackboard. Okay, so you can go out there and see how it's done. You can see how it's done. Look at the programming for that. Look at the Excel spreadsheet for the programming.
Hey, Professor, I just had one quick question. When you actually ran the random number sampling, could you just do that really quick one more time to show me the parameters you used and how you determine those parameters?
Okay, so we'll do data.
Yep.
Data analysis.
Mm-hmm.
Random number generation.
Yep.
Okay. We just wanted one. Q. I wanted to run 10 iterations, normal distribution with a mean of 27 and a standard deviation of 4.
Yeah, how did you determine the mean and standard deviation?
We just made them up.
Okay. So
yeah,
in a real application though, like how would we usually determine, is that just like, are those just general things that we would find through our data kind of analysis?
Yeah, you would have to find that through your data.
Okay.
You'd have to do a study to figure out what those were.
So you'd have a sample, let's say 20 people in a population study or something like that, and then you already have these data points, and then this is and so you would generate random numbers and like this whole model based off of the sample data you have.
Yes, exactly. Okay. Yeah.
Cool.
Yeah. So this is very simple simulation analysis. Okay, very simple. But even if it's more complicated, you know what the process is. The only thing that's going to be more complicated is this part right here. whatever the equation is. But after that, all of these type of calculations, are normal, Okay, so I got a couple more to do. I'll do those offline. But other than that, we're finished for today. I obviously went very fast, and I'm sorry. But I'm going to